Welcome back, everyone. Ready for a holiday deep dive? This one's a little different.
No.
We're not just exhibiting reality with tech. This time we're questioning the fabric of reality itself.
Oh,
You ready to stretch those whiskers?
always.
Good.
Yeah.
Because we're diving deep into cosmology. You shared some research that really challenges the dominant model of the universe. That's like ultimate extended reality exploration, right?
Absolutely. We're talking about the foundation of everything, the so-called lambda cold dark matters model, or CDM for short. It's the top cat right now, you could say.
CDM. Sounds a bit like a hairball to me. But before we get to the challengers, can we quickly recap what this model even says? I'm picturing a timeline of the universe, right? We started with a big bang, rapid expansion, and then things slow down thanks to gravity. Classic story.
Yeah, that's the basic idea. At least that's what everyone thought until the 1990s. Then observations showed something totally unexpected. The universe, like a playful kitten, decided to throw a curveball.
Oh, but
Instead of slowing down, the expansion was speeding up.
hold on. So the universe is hitting the gas instead of the brakes? That changes everything.
It really does. Threw everyone for a loop. Scientists had to come up with a new explanation. And that's where dark energy enters the picture.
Ooh, dark energy.
Yes.
Sounds intriguing, but spooky.
Imagine an invisible force making up like 69% of the universe's total energy. That's what's driving this crazy acceleration. We can't see it, can't measure it directly, but we see its effects.
An invisible force controlling everything. Sounds like a cosmic ghost story to me.
It's definitely a puzzle. What's even more fascinating is that the idea of this force was actually proposed by Einstein. Not exactly how we understand it today, but still, he called it the cosmological constant, represented by the Greek letter lambda. Back then, everyone thought the universe was static, not changing, So Einstein used lambda to keep the universe from collapsing in on itself.
So Einstein was trying to make the universe fit his idea. Classic case of positive thinking, huh? But the universe had other plans, so what happened to this lambda thing?
When Edwin Hubble observed the universe's expansion in 1929, Einstein famously called the cosmological constant his biggest blunder. He abandoned the whole idea.
Ouch, poor Einstein.
But then, when this accelerating expansion was discovered, scientists had to go back to those old equations.
You're kidding.
And guess what? Einstein's lambda, this supposed mistake, made a huge comeback.
Talk about a cosmic comeback.
Right.
So lambda, now representing this dark energy, became like a foundation of the current standard model.
Yeah.
The CDM we were talking about.
Exactly. And it's been incredibly successful, I have to say, explaining lots of observations. But like a curious cat who spots a new toy, there's a challenger, the Timescape model, and it's causing quite a stir.
Ooh, a challenger appears. This is getting good. So tell me, what's Timescape all about? What makes it so different from OCDM?
The key difference is how they see the universe on the biggest scales. ACDM assumes the universe is perfectly smooth when you zoom out far enough, kind of like a perfectly spread layer of catnip across the floor.
But we know that's not really true, right? The universe has all these clumps, dense clusters of galaxies, and then huge empty spaces in between. More like a giant cat toy, all jumbled up.
Precisely, and that's where Timescape comes in. It embraces this cosmic web we see. It says these clusters and voids are more important than we thought.
Okay, I'm with you so far. But how does this clumpiness get rid of the need for dark energy? It's not like those empty spaces are pushing the universe apart, right?
That's where things get really interesting. Timescape proposes a radical idea. What if time itself flows differently in those empty voids, compared to those denser galaxy-packed areas, Basically, time runs faster in the voids.
Whoa, wait, time running at different speeds. Now we're talking. This is getting wild. So how does that explain this accelerating expansion everyone's saying?
It all comes back to Einstein, really. His theories of relativity, specifically how gravity warps space, A&D time. In those voids, gravity is weaker, so time would naturally flow faster there. This difference in time flow across the universe could look like, you guessed it, accelerated expansion.
Wow, okay, my brain needs a moment to process this. It's like a cosmic game of tag, where the rules change depending on where you are. So no dark energy, just time playing tricks on us.
That's the gist, yeah. It's more complicated, of course, but that's the core idea.
This is blowing my mind. But how do we know which model is right?
Yeah.
It's not like we can just measure the universe with a ruler.
That's where those amazing type Ia supernovae come in. Exploding stars, basically. But they have a very consistent brightness. They're like our standard candles in the darkness of space.
Ah, so like those glow-in-the-dark cat toys, but way more useful.
Exactly. And by observing how bright they appear at different distances, which we figure out based on how much their light is redshifted, we can map out the universe's expansion, like a history.
Okay, I'm following. So what's this supernova data telling us? Is Timescape ready to take over and become the new top cat?
Well, a recent study looked at this data, and they found a strong preference for Timescape, statistically speaking, especially when looking at lower redshifts. That's where those voids have a bigger impact.
Ooh, sounds like Timescape landed a good hit.
Is CDM going to give up its title?
Not so fast.
What?
CTM still works really well at those huge scales across the entire universe, where everything looks smoother and those time variations average out. So for now, it's more like they're sharing the cosmic litter box, you know?
A cosmic truce. I love it. Okay, so even our understanding of the universe is changing all the time, just like chasing that red dot. But before we get too lost in the weeds, let's pause here. We'll pick up this thread in part 2 of this 3-part deep dive. We'll delve deeper into this statistical battle and see what other surprises the universe has in store for us. We'll come back to our cosmic playground, everyone. Last time, things got pretty wild. We were talking about 2 models of the universe. The one we all know, CDM, with its mysterious dark energy, and the up-and-comer, Timescape, which says time itself might be behind this accelerating expansion. It's a lot to wrap your head around.
It really is. It's like, which toy is more exciting? The one you know and love, or that shiny new one over there? Perfect analogy. But we need more than excitement. We need evidence. So where does this statistical battle stand? Does Timescape really have what it takes to beat SCDM?
Well, the study we mentioned used something called Bayesian statistics. It's a way to see which model is more likely based on the evidence we have. Kind of like a cat, deciding which way to tip a box over.
So a calculated pounce. What did this analysis show?
Timescape won, basically. Especially when looking at what's happening closer to us, at lower redshifts, that is.
Lower redshifts meaning closer in space and time.
Right.
So those voids where time might be faster, they have a bigger impact nearby.
Exactly. It's like ripples in a pond. You see them better near where the stone dropped.
So is Timescape the winner? At least in our neighborhood.
It's strong evidence, but the debate isn't over. Remember, SCDM still explains things really well at those huge universe-spanning scales, where things average out more.
It's like a cosmic tug-of-war, each model pulling on a different end of the universe. But it's not just about the numbers. These models represent totally different ways of seeing things.
Absolutely. It's like describing a cat's jump. You can talk about its grace and how effortlessly it moves, or you can write down all the physics equations.
Both true, but different ways of understanding. So, back to Timescape. What makes it so statistically strong, especially close-up?
Remember those supernovae we talked about? Those exploding stars we use to measure distances? When they factored in how clumpy the universe is, like Timescape predicts, those supernova measurements suddenly made a lot more sense.
So it's like trying to judge distance in a forest, except it's giant clusters of galaxies blocking our view.
That's a great way to put it. Timescape says that all that matter out there, those clumps and voids, they change how we see those explosions.
Wow, this is really making me think differently about the universe. But let's be fair to ECDM. Why does it work so well at those larger scales?
Well, think about it. When you're far enough away, all those individual clumps, those galaxies and voids, they kind of blend together.
Like a painting, maybe? Up close, you see the brushstrokes?
Exactly, but from far away, it looks smooth.
So at that scale, the universe does look homogeneous, and CDM makes sense again.
Right. Plus, CDM has explained so much other stuff really well, like the cosmic microwave background radiation that's like the leftover heat from the Big Bang.
It's got a strong track record. So we're left with this puzzle. 2 models that seem contradictory, both with good points and bad points. This is where things get really interesting.
Definitely. It's time for some serious scientific detective work. We need more observations, more data from those supernovae, better models to test all this.
And who knows what else we'll discover along the way. But alas, our time for this segment is up. We'll be back for the thrilling conclusion in part 3 of this cosmic caper. Until then, keep those whiskers twitching and those minds curious. And we're back for the final round of our cosmic showdown.
Yeah.
It's been a wild ride through the universe, hasn't it? We've got these 2 models vying for the title of Champion of the Cosmos. CDM with its mysterious dark energy. And Timescape, saying time itself might be the real culprit behind the universe's expansion.
Yeah, it's been a lot to unpack.
We've seen how Timescape has some serious statistical power. especially when we zoom in on those closer parts of the universe, where those big, empty voids and their time-bending ways seem to have a bigger impact.
Right, those voids really shake things up.
But then we've also got CDM, still holding strong at those massive universe-sized scales, where those individual clumps and things smooth out.
It's like they each have their own territory, you know?
It's almost like we need both models to really grasp how complex the universe is.
That's a great point. They each offer a piece of the puzzle.
And that brings us to the big question, the one everyone's waiting for. Which one wins? Which model will reign supreme? Come
Well,
on, spill the cosmic beans.
the truth is, we don't know yet.
Oh, come on. You're killing me with suspense.
But that's the beauty of science, isn't it? It's all about exploring, asking questions, refining our understanding, just when we think we've got it all figured out. The universe throws us a new mystery.
Yeah, that's what keeps things interesting. This whole debate has been a good reminder that what we think is true today might be totally overturned tomorrow.
Absolutely. It keeps us humble.
This deep dive has also shown how important it is to look at things from different angles. CDM and Timescape, they both have their strengths and weaknesses. By considering both, we get a much richer understanding of the universe.
It's like watching two cats play with the same toy. They might have totally different styles, but you learn more about the toy by seeing both.
Love that. So what are the big takeaways from all this, you think?
Well, I think the main thing is that we're still learning. The universe is this vast, mysterious place. Our understanding is constantly changing. It's like we're on this never-ending adventure.
It reminds us to stay curious, right? Keep asking questions. Be open to new ideas, even if they sound crazy at first.
Exactly. It's all about that sense of wonder.
And this whole debate also shows just how clever humans are. We come up with these incredible models and theories to explain the universe.
Even if they turn out to be wrong, or just partly right, the process itself teaches us so much.
So what's next? How do we settle this cosmic battle once and for all?
More research, of course. We need better observations, more data from those supernovae, and even smarter models to test all these ideas.
Like giving our scientific curiosity a bigger, better playground.
Exactly, and who knows what we'll find along the way.
Maybe the universe is even weirder than we thought. Maybe there's another model out there, even more radical.
Or maybe the truth is somewhere in between these two we've been talking about.
The possibilities are endless. That's what makes it so exciting.
We're pushing the boundaries of what we know, venturing further into the unknown.
Unraveling the secrets of the cosmos, one mystery at a time.
Perfectly said.
And on that note, dear listeners, we've reached the end of our cosmic exploration. We hope you've enjoyed this deep dive into cosmology. Remember, the universe is full of wonders, just waiting to be discovered.
Maybe one of you listening will make the next big breakthrough.
Until next time, may your curiosity stay sharp.
And your minds continue to purr with wonder.